Hello Year 12s and welcome back to Mathematics. In this video we're going to be looking at the last section on this section of descriptive statistics. So this is on page 45 and we're looking at this section called, where we're looking at a thing called the line of best fit. Now in the last lesson we talked about correlation and we talked about how on a scatter plot we can actually observe whether or not two variables are related and we could actually measure that relationship or correlation using Pearson's correlation coefficient. And we went through how to do that and put it on a calculator, and then we also described the type of correlations that we have. What we're looking at here is actually creating from a scatter plot or from a set of bivariate data an equation for a line so that we can actually start to notice trends that might happen with our bivariate data. So if we wanted to make a prediction about from our bivariate data about something in the future or something that's happened, make a prediction based on the data that we have from a bivariate plot, we can actually do that in a more accurate mathematical way. And that's what this line of best fit is talking about. So let's go through what this is about. So this is on page 45 in your blue booklet, and this is definition 35. So the line of best fit or let me try to say that again. The line of best fit or trend line is a straight line that provides a representation of all the data points in a scatter plot that has a linear correlation. So what this means is if we have a scatter plot and we have a few dots that look like this and like this, for example, this is an example of like a weak or moderate correlation. What we can do is we can create a trend line. So notice here it's a linear relation. It's kind of going upwards in a linear shape. We can create a linear, we can create a straight line that goes through it and it kind of represents all of those data points. And it kind of helps us to create, observe trends from it. Now here, I've got a few important notes underneath. Draw a line of best fit by eye. So this is if we are drawing it by eye. And this involves fitting a line such that the distance of the points from the line is minimized. So what we want to do is want to ensure that we create a line where the distance between all of these data points, so all of these each separate data points and our line is minimized. We don't want to have we don't want to create a straight line which is so far away from one of our data points that it doesn't actually accurately represent it. So for example, if I drew a straight line that went this direction, that wouldn't be an accurate trend line because you've got all these points up here which is really far away from my trend line or my line of best fit. The second thing is then we want to have approximately same number of data points lie above and below the line. In order for our trend line or our line of best fit to be an accurate line of best fit for our bivariate data, we need to have a same number of points above and below. So here, this is what I'm going to try and do. Ooh, let's see if I do that. So here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then on the other side I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I somehow magically did that, and you know that never works. Okay, so you want to have approximately the same number of data points either side. And the final point is, here, the line does not need to pass through any data points. Now, sometimes you might have a data point that lies directly on the line of best fit, which is great, but it doesn't need to necessarily pass through any points. You could just, as long as it's kind of like in between and manages to follow the previous two criteria, that's fine. So, and a good example of this is if I had, let me just draw my line of best fit first and then we'll show you. So if I have a set of data where it looks like this, and we just got dots either side of my line, and they're even like that. Well, this line of best fit, it doesn't have any data points on it, but it actually works as a line of best fit because it minimizes the distance between the points and the line, and also we have the same number of points above and below the line. Okay, so that is what a line of best fit is, and if we're drawing it by eye, that's what we want to try and do. That's if we're trying to draw it by eye. But like I said last lesson, it's nice to talk about when we talked about correlation. It's nice to talk about correlation just like generally, but it's also nice to actually have an accurate description using mathematics. And so what we can actually do is we can create a trend line using mathematics in to create a very accurate trend line based on the data that we have. And so what this line is called is the least squares regression line. So it's quite hard. I keep saying this wrong anyway, and I mix up the words, but it is the least squares regression line. So this is a mathematically determined straight line that best fits the data set by minimizing the squares of the vertical distance from the points of a line. So what we're doing here is this, when we calculate this, what this particular calculations do, and we don't actually need to know the calculation, we do need to actually know a few things here, we're going to go through in a moment, but we don't need to actually go through and calculate each individual thing. We can chuck it straight into a calculator and find it for us, which is really nice. But what we're trying to do is, if I have a data set and I've got a whole bunch of points, so something like this, what this least regression line does is, in order to create this least regression lines, it takes all of the distances between the line and each of the data points, then it squares them, and then what it tries to do is try to minimize all of these numbers. It tries to minimize all these numbers as best it can in order to create that straight line. Now, this next part, because it is a straight line, it follows the same rules as a regular straight line. So it follows the equations of our straight line. So here, it's going to be in the form of y is equal to mx plus b, which was the equation of a line. And m, as we said in our linear relationship, when we started talking about this all the way back in year 11 at the start of the year, m is just the gradient of our line, and b is the y-intercept. Now, when we look at the least squares line of regression, it's not quite as simple as just m and b. We're actually going to find equations to find what my gradient is and what my y-intercept is, and then we can actually put these into an equation and figure out, and using this create the line, the equation for the least squares regression line. So that's what we're going to look at in the bits below. So here in this section here, we talk about the gradient of the least squares regression line, and also the y-intercept of the least squares regression line. So this is what we need to do if we're trying to find these two particular things. So let's start off with the gradient. Now, the gradient of our least squares regression line, so I had m was my gradient. What this is made up of is a few different things. Now, first part that is made up of is r. And r, if you have a look here, r is a familiar concept that we looked at last lesson. R is just Pearson's correlation coefficient. And so when we're trying to find our equation for our gradient, if we want to just actually calculate what that gradient is by itself, we need to find the correlation coefficient, so R. Just like we did last lesson, we went through how to actually put this in a calculator. And on top of that, we need to multiply it by a fraction. And now this fraction involves two things. The first thing is, and let me pick a next color, so here we go. The first thing is going to be sigma y. Now, sigma we've already talked about as well when we looked at univariate data. Now, just to think about this for a second, what we said was bivariate data is when we have two variables. So my x coordinate, x values are one variable, and my y values are one variable as well. And so here are a whole bunch of different points. Now, what happens is each one of my points is actually made up of two data points. So, for example, this one has an x value that's connected to it, but it also has a y value that is connected to it. And so here we can actually separate all of our data points. So all our data points, last lesson we went through that example at the end where it was a whole bunch of different coordinates, right? We had like a whole bunch of different coordinates, 2, 1, 1, 2, and so on. What we can do is actually we can split it up into two separate data sets. We can have the x coordinates being our x data set, our y coordinates being our y data set, and using those we can actually calculate the mean of those data sets and also the standard deviation, which is something that we did a couple lessons back as well. And so here sigma y is just the standard deviation of y. And so here sigma y is my standard deviation of y. And at the bottom of this fraction, hopefully you could see it, is, and I'm going to move this up so we can actually see it a little bit better. Ooh, and I'm just going to erase that. Let's try this. Excellent. Above that, we've got, below that, we've got sigma x, which is just my standard deviation of x, the x variable. And so here we can actually calculate these using our calculators quite easily. And I'll show you how we can do that. And so this is a formula if we want to find the gradient of our least squares regression line. Okay, underneath is our second part, which is our y-intercept of our least squares regression line. Now, the y-intercept, we need a few different things for this particular part. For this particular y-intercept, well, actually, up above, we actually wrote it as b, and I realized I already used green, which is not great. But here, b was my, from that equation up above. What we need in my y-intercept for my least squares regression line is three things. The first one is down at the bottom here, y with, I'll pick a different color so you can actually see it. Y with a hat. Now, whenever we see something with a hat, what is that measuring? That is measuring our average or the mean. So here, y hat is just our mean. And we're going to subtract from that. We're going to subtract m, which is the gradient that we found in the previous part up here. Gradient. And we're going to multiply that by x with a hat. So x bar, which is just our mean of the x variable. So x bar. And so that's how we find the gradient and the y-intercept of our least squares regression line. Now, what's going to happen often is we're not going to actually use these calculations, these formulas fairly often. We still need to know them because sometimes a question might be asking us to actually derive it based off of information that we're given. So we might get given the standard deviations and the correlation coefficient, and we need to calculate it. But we can actually, what we're going to often do is actually use our calculators to calculate this. But just to put this all together, if you flip over the page, the equation for the least squares regression line, so we wrote it earlier as y is equal to mx plus b, but it can also be written as in this form. Y is equal to a plus, let me pick a different color, b x. Let me keep it consistent with all our coloring from earlier. A is our y-intercept, as it turns out, and b is our gradient. Now, the reason why we've actually changed letters here is because on your calculators, a and b actually show up in that statistics, in that statistics menu that we actually looked at last lesson. Now, if you remember, when we fit in bivariate data, you can go to the statistics menu and you'll get this 5 button, reg. And if you press 5, A and B actually rock up there. A and B are right here, and we can actually use this for to calculate the least squares regression line just straight off by finding those values. So here, A is our y-intercept that we found in the previous part, and B is our gradient that we found from the previous part. And so here below, we've got the steps on how to do that. Now, I'm going to go through this with one of the examples in a moment and actually show you what this looks like. But what we basically do is very similar to last lesson. The first thing we need to do is actually enter our data points into our calculator. So just using, we go through and we enter each step of our data. So here, that is what these first two steps do. When we're using bivariate data, when you put it into our calculator. Then, when we want to find the y-intercept is A. So on our calculator, if we go to that stat menu, so the stat menu, if we press 1 for A, that will give me the y-intercept. And then if I want to find the gradient, I'm just going to go to that same stat menu and I'm going to press B. And that will give me the gradient of my least squares regression line. Okay, let's go through an example where we actually have to use line of best fit and also calculate this least squares regression line. So let's flip over the page. Oh, actually, we've got a bit more to go through. I apologize. The important note underneath. The accuracy of the predictions increases with correlation coefficients closer to positive or negative 1 with greater number of data points. So when we create this least squares regression line, what it can actually help us to do is, what I said was we can actually observe trends. So if I have a data set, something like this, and I have my least squares regression line, what this can help me to do is I can make predictions based on this least squares regression line. So for example, if this was like heights and weights, which is the example I always talk about, height and weight, what this least squares regression line can actually help me do is, okay, so let's say I have someone who is 174. Based on this data that I've collected, what should I expect their weight to be? So I can just go to the least squares regression line and then just read off the value here, and that will tell me what their expected weight is. Or if someone is much higher, so let's say like, oh, over here, I have someone who's 2 meters tall. What should I expect their weight to be? It also works in the opposite direction. Like if I have someone, if I say, oh, there's someone who is 80 kilograms, what should I expect their weight to be, height to be? And so that's how we can actually use this least squares regression line. Now the point here is basically saying if the predictions that we can make with this least squares regression line, it gets a lot easier to do if our correlation coefficient gets close to 1. Now, if you remember, if our correlation coefficient gets closer to 1, what this means is that I can basically form a straight line of dots. So here, if I have a correlation coefficient of 1 or -1, which was just the opposite direction, like this, it forms a straight line. And so my trend line, if my correlation coefficient is closer to 1, is basically going to get really close to those lines. Really close to those dots, I mean. And so that will help me in, if I have a particular data set which has a correlation coefficient close to 1, that means that my least squares regression line is going to be super accurate in telling me those pieces of information. The other thing is, if I have more data points, the more data points I have, the easier it is to get a better reading as well. So that's what this first point is saying. Now there's 2 steps that we're talking about. Now there's 2 kind of like operations that you can do with reading off a graph. The first one is interpolation. Interpolation predicts the value of a new data point within the existing range. So back a couple of examples ago, so when I did that height and weight thing, if I have a data point that is over here, notice it's within my data set. My data set goes from this point to this point. So here, interpolation is if I want to make a prediction inside my data set. Extrapolation, which is the other one, so interpolation, and the other one is extrapolation, is we want to predict the value of a new data point, which is outside the existing range of data points. So extrapolation is if I go, okay, I've got a new data point which is over here, which isn't inside my existing data, and I want to make a prediction about it. And which is why these least squares regression lines are used. Mathematicians and people want to find out information about stuff that they don't know. And so here, using this, they can actually make predictions about new data that they don't know anything about. Okay, now the important note here. Extrapolation can be misleading since data relationships often do not continue without changing unpredictably. The world is a really random and chaotic place, and so if you make those predictions outside of your data range, you're not actually going to be super unsure. Things could suddenly change. So like, for example, after, let's say like this, the high score was 180 centimeters, and after 180, suddenly everyone's weights all just tapered off or something, or like they suddenly started decreasing. We don't know. We don't know. And so extrapolation becomes sometimes a little bit misleading. So extrapolation should not be used to predict values far outside the range of existing values. So I shouldn't use this graph, for example, to predict the height of someone who is going to be like, for example, 5 meters tall. For a few reasons. One, I don't think, one day maybe we'll get there. But 2, it's just like, it's not got to be very accurate. This is like a massive outlier which just doesn't sit in with the rest of the data, and so you're not going to be able to make an accurate prediction here. Okay, so let's go through an example of this. This is example 28. Example 28, which is from 2015 General 2 HSC 28 paper. The shoe size and height of 10 students are recorded. So here are the shoe sizes and heights in the table here. And we've got, and we're going to be using this for the following questions. So the first part, complete the scatter plot and draw a line of best fit by eye. Now notice here in my scatter plot, I've already got 1, 2, 3, 4, 5, 6 data points. The first 6 data points they've already done for us. So I've already done this one, this one, this one, this one, this one, and this one. What we need to do is just put on our remaining 4. So all we need to do here is just look at the X values and then look at the Y values and just put them in. So the next one was 10, 190. So I'm going to go to 10 and 190 and put across there. 11, 185. Put across there. 12, 200. And 12, 195. Like so. Okay, that was our first step. Excellent. We've done that. Now next step, so we've completed the scatter plot. The second bit is we want to draw a line of best fit by eye. So here we aren't actually calculating that least squares regression line. We're going to actually do that just for the sake of this question and just to get some practice. But we just need to draw a line of best fit by eye. And so with this, what we want to do is probably get our ruler to actually help you out. And we want to just ensure that half of the points are above and half of them are below, and that we minimize the distance between the line and our data point. So here, notice I've got here we've got 10 data points. So I kind of want to have a line which has 5 above and 5 below. So if we have a look here, I'm going to just go somewhere around. So the 5 lowest ones happen to be here, I believe. Okay, and if I just line it up like that, yep, that's kind of fairly accurate. You've got most of them, they're kind of equally distant from the line. If anything, I might go even a bit lower, just so that I can ensure my ones below are closer. And I'm just going to draw a line through there. So there we go. So notice here, half my points are above. So 1, 2, 3, 4, 5 are above, and half of them below. 1, 2, 3, 4, 5. And I've tried my best to kind of minimize the distance between the line and those points. Okay, so we've drawn our line of best fit. Done. There we go. Here, what we're trying to do is just create a line where you have half your points above, half of them below, and you kind of minimize the distance between those points and the line. Okay, so I've drawn my data set, I finished the scatter plot, and I've also drawn the line of best fit by eye. The second part, use the line of best fit to estimate the height difference between a student who wears 7.5 shoe and one who wears a size 9 shoe. Okay, so for this one, we want to find the height difference. I'm just going to underline a few keywords. Height difference between a student who wears a 7.5 shoe and a 9 shoe. Now, 7.9 and 9, these are the sizes of shoes. We're not just going to subtract the two because we want to find the height difference. So what we want to do is we want to use our line of best fit and find the height of a student who is 7.5, who has size 7.5, and then we're going to find the height of a student who is size 9. So I'm going to go to my data set and I'm going to find where shoe size 7.5 is. Shoe size 7.5 is over here. Let me try that again. Over here. Okay. And so what I'm going to do is I'm just going to draw a line. Now, just to help me out, I'm just going to draw a dotted line from my point to my line there. And so once I've done that, from my 7.5 to my line of best fit, and I'm just going to read off what, read off what the height of the student is. Now, if you have a look here, it kind of looks at roughly 164. So here for part 2, the height of the student, so 7.5 shoe size, is going to correlate to someone who is, I'm just going to draw a straight line here, correlates to someone who is 164 centimeters tall. And once we've done that, we're just going to repeat that process, but with my size 9. So I'm going to go to size 9, which is over here. Oh, let me try that again. Over here. And I'm just going to grab out my ruler and once again, draw a straight line. And just do a dotted line here. And there we go. Okay, and we have this point here. And so that is, to me, that kind of looks roughly 175-ish. So size 9 shoe is 175 centimeters. And so if we want to find the height difference, all we need to do is just subtract the two. So therefore, height difference is equal to 175 minus 164, which happens to be 11 centimeters. Okay, so that's how we can use our line of best fit to find information based off of the line of best fit. Now, what we've done here is this is actually based off of my line of best fit that I drew by eye. Just for the sake of practice, let's actually have a go at finding the equation of the line of best fit using the least squares regression line. So what I'm going to do is I'm going to actually put this data into my calculator. So I'm going to grab my calculator out and I'm going to go to the bivariate, let me try that again, bivariate data mode. And so here I'm in the bivariate data mode when I press 2. I'm going to now put in all my data points into this set. Now, when we did this in class, what I said was to make it easier, just go through all of the values of X first and then go through all the values of Y. So here I'm going to go through all the shoe sizes first, and then I'm going to go through the height next. So here I'm going to go 6 equals 7 equals 7 equal 8 equal 8.5 equal 9.5 equal 10 equal 11 equal 12 equal 12 equal. And so we've got our 10 students here and their height, shoe sizes. Now we need the height: 155, 150, 165, 175, 170, 170, 190, 185, 200, and 195, and they both line up. And so I've put in my data into my calculator. I'm going to press AC just so I can clear the screen. If I'm trying to find the least squares regression line using our calculator, we're just going to go put in this into the equation: y is equal to a plus bx. So I'm going to find the values of a and b. So here I'm going to press Shift 1 for the stat menu and press 5 for reg. So that's for our bivariate data. And so here I'm just going to press 1 for A. And so here I've got A is equal to this value, 109.66. I'm just going to store that in my calculator for now. Ooh. Ooh. Going to store that in as A. So here A is equal to 109 what was our value? 0.667 and so on. Okay, and I'm going to do the same thing for B. Now B, I'm just going to Shift Stat and Reg. I'm going to press 2 for B, and I'm going to press equal, and that gives me 7.23. Now, what I've done is actually I've stored these two values as A and B on as those pink letters. So here I'm going to Shift Store B because it doesn't automatically do this in your calculator. The reason why is if I want to actually do calculations with linear line, it's actually quite easy to just pull those out. So what I can do with my least squares regression line is I can make those same predictions, same interpolations, but actually doing it in a much more accurate way. So I'm going to actually put these two values, 7.5 and 9, into my equation. So what I'm going to do is I'm going to go for 7.5, that is a shoe size, which is just an X value. So I'm going to just put that in. So I'm going to go Y is equal to A plus B times 7.5. And so I'm going to put that in my calculator. A plus B times 7.5. And so the least squares regression line will actually tell me that a student who is has a shoe size 7.5 is actually roughly 163 centimeters and 163.92 centimeters tall, which isn't super far off of what we actually did by line. So our by line one, not bad. So 163.9, I think it was 92. Okay, we're going to still do the same thing for our student who is 9 centimeters tall, has a shoe size 9. So we're going to do Y is equal to A plus B times 9. And so we're just going to do this exact same thing. This is actually quite nice for me because I can just replace 7.5 with 9 and I get 174.77. So 174.77. So here I'm just going to actually round this, so this becomes 164 and this becomes 175, which is exactly pretty much what we got with our hand-drawn line of best fit. Sometimes your line of best fit is going to look perfect and it's going to be exactly like that, but other times it's not going to be as super accurate as this. So you're going to just, depending on the question, usually there will probably, because in advance, they will probably ask you to find this linear least squares regression line just using mathematics, and you can actually calculate it a little bit more accurately. So that's what you can do there. Okay, so hopefully that makes sense in actually calculating the least square regression line. Oh gosh, I can't say it. And also actually creating a line of best fit and interpolating data off that. Okay, part 3. A student calculated the correlation coefficient to be 1. for this data set. So I'm going to underline that. Correlation coefficient to be 1 for the data set. Explain why this cannot be correct. Now, when you see a correlation coefficient of 1, we call that a perfect positive correlation. So what that should look like is this. If you have a look at our data set, do we have something that looks like that? Unfortunately, we don't. So here, as the data points do not form a straight line, it does not have r is equal to 1. This has only a, and we can describe it a little bit more. We can say, okay, it kind of has a strong positive relationship. This is only a strong positive correlation. That's what we can say here. Okay, so that's how we can actually answer this first example here. We're going to go over the page and have a look at another example. So here, I'm going to actually go look at this one. This is from the VCE paper. Now, with the least squares regression line, a lot of this work is actually a lot of stuff similar to the stuff that we looked at in linear relationships. So here, that's what we're going to be doing in this example. Let's have a read. The scatter plot below displays the resting pulse rate in beats per minute and the time spent exercising in hours per week of 16 students. The least squares line has been fitted on the data. What we need to do in this question is, so here we've got our scatter plot. Notice we've got our scatter plot in here, and they've also drawn on for us the least squares line of regression line. So what we need to do in this question is we want to find, let's actually read it, the equation of this least squares line is closest to which of the following. So what we want to do is find out which of the following is kind of the best way of accurately representing this line here. So we've got a whole bunch of different equations that represent the resting pulse rate. Now, if you remember, the equation for our least squares regression line is y is equal to a plus bx. Now here, a is our y-intercept and b is our gradient. So all we need to do is just like a normal linear relationships kind of question. We just want to find what the y-intercept and the gradient is. So actually, let's start off by looking at a. Now, the y-intercept, we just have a look at where it is over here. So y-intercept is all the way over here. And so if you have a look at that, that's roughly 7.2. And so from there, what we can do is, okay, we can immediately get rid of a few of these answers now, can't we? So for example, I can get rid of this one C, and I can also get rid of this one D immediately, because both of them don't have that y-intercept. So the first thing I would be looking for is that y-intercept if possible. Okay, second thing is then we start looking for the gradient. Now have a look at this gradient. Is this gradient positive or negative? Well, it's going downwards, which means that this is a negative gradient, which means I can also cancel out another one of these answers. If you have a look in this last one, it has plus 1.1 times the time exercising. That would suggest a positive gradient, which means I can also cancel out this one, E. And so here, because of the gradient is not positive, I can get rid of that number there. And so we're left with these two here, A and B. 6.7 minus 0.9 or 6.7 minus 1.1. And so what we need to do as our final bit is we need to actually go and calculate our gradient. Now gradient, which we calculated from year 11 and also hopefully from year 10, from 8 to 10, is the gradient of a line is the rise over run. And so what we want to do is we want to find the rise, and in this case it's going downwards, so we're going to go, the rise will be downwards, and we're going to divide that by the run, how many units it goes across by. So what we want to do is we want to find a point which is on our least squares regression line. Now here, if you have a look at the diagram, there's a point which is quite easy to see. Over here, we have a point that's straight up on our least squares regression line. So we can actually use this point to help me find the gradient. So if you have a look, I'm going to go, okay, my run is my x, how far I go across in x units. So here, my run is from 1 to 3, so that's a run of 2. And then we go downwards but to 65. So here, this is the rise is going to be 65 minus 67.2. And so that is negative 2.2. And so when I've done that, I can just put in these values into my calculation. So the rise is negative 2.2. And with our run is, what do we have here? Run is over 2. Okay. And so there we go. We've got this. And so this becomes negative 1.1. And so here, my answer is going to be B, just based off my gradient in this step here. So that's how we can actually answer these questions. There's a lot to do, if we're dealing with our line of best fit, it has a lot to do with linear relationships. So we're going to need to apply a lot of those. We need to apply a few of those skills that we have from there. Okay, let's go through another question. And I'm actually going to, from here, I'm going to actually have a go at a few more questions with you guys in class. So what I'm going to do is I'm actually going to have a go at this one here, 2018. This one here. Question, example 31. Example 31, this is from the 2018 VCE paper, and it says the following. The statistic analysis of a set of bivariate data involving variables x and y resulted in the following information displayed in the table below. Now, if you have a look in this table, they give us the mean, standard deviation, and the equation of the least squares line. So here, they've given us this information already, and let's read what the question is asking us to do. Using this information, the value of the correlation coefficient R for this set of bivariate data is closest to. Okay, now, if you have a look, none of this stuff has anything to do with R that we looked at before. How can we go about actually figuring this out? Now, this question actually involves a few different bits. Now, if you remember, we can actually go, if you remember, R is actually used in the calculation of finding the least squares regression line. A couple of pages ago, if you remember, what we said was that the gradient of our least squares regression line, M, is equal to R times sigma y over sigma x. So if I want to, so here, this is how the least squares regression line is related to our correlation coefficient. And so if you want to find R, all we need to do is just rearrange this equation. So all I'm going to do is I'm going to rearrange it. So that gives me, if I move R to the other side, that gives me R is equal to sigma y over, oh no, actually, I'm going to move R, I'm going to move this fraction here over, this guy here over to the other side. So that means I've got M times sigma x over sigma y. Now, let's actually go about and figure out where where all of these values come in. Now, the first part is M. Now, M is just the gradient of my least squares regression line. So if you have a look, where can I find that in my table? Well, they give me the equation of the least squares line, which is right here. So if I want to find M, I just need to find where that gradient is. Now, the gradient is just the coefficient of x, which just happens to be this 1.31. So here, if I want to find R, if I want to find M, I'm just going to sub in 1.31 times. And the next part I need to find is sigma x and sigma y, which is great for us because we actually got all that information here. So all I need to do now is I just need to substitute sigma x, which is 2.33, over 3.24 for sigma y, and I can just chuck this straight into my calculator. So here I'm going to go, okay, 1.31 times, yeah, that's fine. I'm just going to go to comp mode so I can do this calculation a little bit easier. 1.31 times 2.33 over 3.24, and that gives me 0.94, which is D. So this is actually working backwards to find Pearson's correlation coefficient based off of the equation of least squares equation. And so that's actually how we can actually use one of the formulas that we introduced earlier but didn't actually apply. So that's how we go about doing this question here. We actually need to go and remember that the gradient of our least squares regression line is found using this formula. Okay. Now we're gonna skip these multiple choice questions, and actually I'm gonna leave that question for next lesson as well. But hopefully this helps you in understanding what the line of best fit is. So we talked about what the line of best fit is, and we actually also went through calculating it using our calculators. In the next lesson, we're going to go through the remaining questions in this in the booklet for this part, and also go through a few more questions where we actually need to calculate and find the least squares regression line. But until then, Year 12s, I hope you have a lovely weekend, and as always, stay safe, stay healthy, stay wonderful, and I'll see you guys next lesson. Bye.